right? They don't just stay. And actually, so it as they get bigger, it becomes unfortunate because it actually is for this reason. So the computation time increases significantly, right? And by how much? Well, you don't have to know this, but like it's big O n factorial. So basically, if it was a 5 by 5 factorial, I mean it's already huge at that point. So just to give you, oh, it's not. Oh, it's because this thing was like. Okay, how about now? Better. Okay, perfect. Yes, I will. I just been really busy at the moment, so I'll do it like right now, right after class. Okay, so actually, if you were to do maybe like even I think what is it like a 25 by 25 matrix and to try to find its determinant, 25 factorial would already like and 20 to the 26 like computations and that would be like if you had a computer that did like a trillion computations per second, it'd still take you like trillions of years for it to finish. So obviously this isn't very practical, right? Even for computers. So basically, what I want to discuss now is how do we optimize finding the determinant, right? So that's what the next theorem will be about, and also what the next section will be about. So also notice this. Notice if the matrix, if A was triangular, right? So here it was almost triangular, right? All it had is that 1 there. So if A was triangular, say like A equals, and it was exactly this except for the 1 there. So so imagine this was triangular. Then all this mess we wouldn't have to mess with it because the determinant of this would just equal the product of the diagonal. So 2 times -3 times 5 times 4, right? Which in that case it was almost immediately. You almost get it immediately. So that brings the next theorem. 3.12. So again, let A be a square matrix, be a triangular. Triangular matrix. Then the determinant of A is the product of the diagonal. Like this. Or, I mean, if you, I think you might find in some places like they do this kind of thing, like AII equals 1 to n. But that just means you just take the diagonal and multiply them. Okay, so it'd be nice if all our matrices were triangular matrices. Unfortunately, that's not always the case. However, we do know a way to make it triangular, right? However, we're not going to discuss that yet because it's a product of triangular matrices, so we still don't know how to really deal with that. But then, this finishes this section. This is a very important result. So remember that. So let's start off now, section 3.2, which is determinants elementary operations. And let's start off with the question. Which of the following is easier to compute the determinant of? Let's say we have A equals this 1, 4, -2, 3, -2, -6, 4, -6, 1, 2, -3, and 2. And then we also had B equals 1, 0, 0, 0, -2, 2, 0, 0, 3, 9, -9, 3, 0, 1, -2, -1, -1, right? After class. And okay, so I mean, according to the theorem that we just stated, which one would be the easiest? Obviously the second one, right? Because that'd just be the product of the diagonal. However, now notice something. A and B are actually row equivalents. Okay, so we could get it into REF form, and there should have been so answer just B. So somehow we can probably try to somehow find a relationship between the determinant of the matrix and its REF form. Okay, if we can find this relationship, then we can almost always compute the determinant with less computations, right? I mean, it just row operations. It's like n cubed type of operation, so it reduces it significantly from n factorial down to that. So let's actually investigate this. So let's state a theorem that tells you basically the rules of how this relationship works. So, okay, yeah. I think you got it. 3.2.1. Let A and B be square matrices. So now we have these three rules. When B is obtained from A by interchanging rows, then the determinant of A is equal to the negative of the determinant of B. Okay, so a minus sign always comes out when you interchange rows. Okay. 2. When B is obtained from A by adding a multiple of a row of A to another row of A. So if you just add multiples of like that elementary operation, so basically what happens is the determinant does not change. Okay, so the determinant of A is equal to the determinant of B. Okay, so that's another one. And then last but not least, what happens when you multiply a constant to a row, right? So when B is obtained from, say, A by multiplying a row of A by a non-zero constant, say C, okay? What happens? Well, the determinant of B is simply equal to C times the determinant of A, okay? That's only if you multiply one row, okay? So now, so now that we know a little bit about the relationship between the row, a matrix and a row equivalent matrix, let's actually try to see how we can apply this to an example to reduce to reduce the time we need to find a determinant. Okay. So let's see. Yeah, why not? Okay. So example 3.2.1. So find determinant of A for 0, 1, 0, minus 7, 2, 3, 14, minus 2, minus 8, okay? So, I mean, obviously you could cofactor expand around the first column. It has the most zeros, but let's actually try to do something that would make us not do that, all right? So let's try to make it triangular, all right? So solution, we will use elementary row operations. Okay. So this is how it works, okay? So start off with your matrix in like this. Okay. Do a row operation. So there's only going to be one that's going to differ a little bit, but let's start off with a row operation. So let me interchange row 1 and row 2, okay? So let's interchange row 1 with row 2. 0, so I'm going to get sorry, hold on. 1, 2, minus 2, 0, minus 7, 14, 0, 3, minus 8. So hold on, let me just check really quick. Okay, so again, according to our thing, what should happen with the determinant? There should be a minus sign, right? So so you have this now, okay? So now, if I want to make it triangular, what should I do in order to make it triangular? Well, let's first, I guess we could, let's see. So let's look at this row right here. Notice that I can factor out a 7 out of this row, right? And that will leave me with a minus 1 and a 2, right? So while I didn't multiply by 7, by factoring out this this 7, so I guess you can say, so we can say factor 7 out of R2. According to, so that one's a result from this guy, okay? So it's not like explicitly, but it's implicitly, right? So you can get this new result. So now you just multiply by 7 of the determinant via this result, okay? So then this becomes 1, 2, minus 2, 0, 1, minus 2, 0, 3. minus 8. Okay? So now from here, let me get rid of that 3 by doing another row operation. So let's do the row operation now. Row 3 goes to row 3 minus 3 times row 1. And according to the third part of it, by adding multiples of rows to another, that does not change my determinant. So nothing comes out. I still have this minus 7. Then should be a minus 2, I believe. Yeah. Okay. So now how do I find the determinant of this matrix? Well, it's triangular, right? So I just take the product. So now it's just going to equal -7 times 1 times 1 times minus 2, which should give me 14, right? So, I mean, okay, so I guess I chose these in order to illustrate the 3 points. So this one's 0.1. So this is 0.3. Sorry, I was pointing to the wrong one when I was pointing over here. So this one was 0.3 right here, and then that blue one was the second point. So I use those 3 in these during this process. Okay. So do you see kind of what now you can do with determinants for matrices using row operations? So interchanging rows gives out a minus sign. Factoring out a constant from a row just literally brings it out to the front, and that's due to the result 3. And then adding multiples of rows to another. Could we factor out a minus 7? Yeah, hold on. Did I? So there was a minus sign here. Yeah, I factor out a minus 7 and can you see that now? Okay. Yeah, it should. Yeah. So there was this minus, and then I factor out a minus 7, and I put 7, so it should be minus 7. My bad. So it should be just positive 7. So that should be minus 14. Yeah. So I factor out a minus 7 without realizing, without doing the. Without realizing that I had another minus sign. But yeah, you're right. So it should be plus 7. But yeah, now do you see how we can reduce our determinants via these things? Okay. So that's nice and all. However, can we do better? It turns out we can, like this. So it turns out that we can do the exact same thing on columns of a matrix. So what do I mean by that? I mean, like, instead of doing row operations, you can call them column operations, but those are the same, right? Adding, multiplying a column by a constant, adding a multiple of a column to another, and interchanging columns. So now are we allowed to do that to the rows, but now we're allowed to do that with the columns, okay? And you'll see the reason we want to do this. So let's do example 3.2.2. So find the determinant of, let's say, A equals -1, 3, 5, 2, -6, -10, 2, 4, -3, okay? And let's call this one C1, C2, C3, right, for the columns now. All right, so let's do the same thing, but with the columns now. So let's take the determinant of that matrix, 1, 3, 5, 2, -6, -10, 2, 4, -3. Okay. So let me do this operation. So let's take column 2 and do column 2 plus 2 times column 1. Okay. So now we have -1, 3, 5, 0, 0, 0, 2, 4, -3. Okay, now let me ask you, what's the determinant of this thing now? Like you should be just trying to do the normal cofactor stuff. Yeah, 0, right? Because if you cofactor expand across the second column, all those things will get a 0 multiplied, and I mean all of them just go away, so it's 0. So so this is important, an important observation for the for this purpose, because if we can get a matrix where we row reduce or column reduce to the point where there's one row or one column entirely made of zeros, then we can stop, right? Because at that point, it's the determinant is 0. So let's do this. So theorem 3.2.2. Yeah, it's 0. It's 0 in this case. So let A be a n by n matrix. If any one of the below is true, then the determinant of that thing of A will be 0. Okay. So what are the 3 things? So an entire row or column consists of 0. Okay. Or 2 rows or columns are equal, or 3, one row or column I think I spelled column up there, whatever. Column is a multiple of another row. Or column. Okay, so any of these 3 happens, your determinant is immediately 0. Okay, so if we go back to our previous example, notice that this one. Oh, sorry, not what I was saying. Notice that this one and this one, the second column was a multiple of -2 of the first one. So that one, I mean, immediately. That one was from the third point in the theorem. If they're the same, why? If 2 rows are the same or 2 columns are the same, why is that give me determinant 0 as well? Because we can row reduce it to, or a column reduce it to, have one. Just basically, you can just take that row, right? If there were like imagine one column is all ones, the second column is all ones, I can just take the first column and subtract it from the second one, and that immediately becomes all zero. That's why you can do that. And then yeah, so basically, yeah, exactly. So they would cancel. Yeah. All right. So. Is that it? Yeah. That's it. Okay. All right. So let's move on to now, and let's apply this to our next example. So again, I should say remark. So typically, we start off with a matrix that does not satisfy the above, but through elementary operations, I'm just going to abbreviate now because I'm tired of writing it, we can turn it into one that does, right? Okay, so let's do an example. So let's see. 3.2.3. So find the determinant of A of 1, 2, 0, 4, -1, 18, 1, 0, 4. Okay. Solution. Again, always start off with the determinant of the original matrix. Okay, so let's see what we can do here. So let's see. So right now it isn't at all obvious, right? That there's a row is either all zeros or one is a multiple of another. So typically what you should do from here is use this strategy. When you're doing when you're trying to find the determinant using row operations, what is the first thing we try to do? Well, the first thing that you should try to do is to try to row reduce it to a triangular matrix, right? Or just REF it. Now, along the way, if you happen to see that a row or two rows are a multiple of each other's or the same, or if one entire row becomes zero, then you can stop and then just immediately conclude that the determinant is zero. So that's what we're going to do here, okay? We're going to assume right now that we're just going to try to make it lower triangular or REFing it, okay? So if I try to REF it, what's the first thing I'm going to try to do? Well, the first thing I'm going to try to do is get rid of that 2, right? So to get rid of that 2, I'm just going to replace row 2 with row 2 minus 2 row 1, right? So this will give me 1, 4, 1, 0, -9, -2, 0, 18, 4. And remember, the determinant doesn't change if I take multiples of one row or another. Okay, but now, okay, so now let's stop here for a second. So now do you see maybe a row that might be a multiple of another, right? Yeah, so the third row is a multiple of the second row by a factor of -2, right? So you can immediately, so multiple. So here you can just immediately conclude that this equals 0 by the theorem. Okay, so again, when you're trying to do this, start off REFing it, and along the way, if you happen to see this observation, stop and just conclude the what the theorem states. Okay. Okay, so very cool. Notes. So let's just make a few observations. So using cofactor, so expansion of, say, a 30 by 30 matrix, right? Just like how we originally tried to do it. This would take, let's say, well, like I said, it takes n factorial, so it'd be 30 factorial, which would be approximately 2.65 times 10 to the 32 computations. Again, if a computer does this, can do, let's say, 1 trillion computations, it still would take 22 trillion years. It would take 22 trillion years. Okay, so that's number one. And then two, by doing this new, result that we did, it would, the computer would just take like a fraction of the time. So using REF, I guess you can say, would take like a fraction of a second for a computer, not for us. But I mean, this is why we do this, right? We try to optimize it in a sense. I mean, I guess technically this is a little bit how numerical analysts, what they do is they try to optimize certain computational, they come. Which one is it? So it's the very first one we did. Remember with the. So hold on. Oh man, we already have 99 pages. Okay. Is this one, right? So is this one where we just take like the like all these like little pieces when you hold on, let's see. When you take when you try to find these M11s, M12s, and then C11s, and then add them all up, that's the cofactor one. Okay. What's the next thing? Yeah, so let's do one more example. And now, and basically after this example, that finishes off this section. So, example 3.2.4. Let's do find determinant of A of, let's say, 2, -2, 1, 3, 1, 0, 1, 0, -1, 0. Three, 2, 2, 4, 2, -2, -1, 3, -3, 0. Okay. So before this would have been a nightmare to compute, right? If we were just done the cofactor expansion. So now let's actually do some of the things we learned, okay? So so maybe let me refine the strategy I mentioned. So before you try to, I guess, to REF it, first try to see if you can like make an entire row or a column all zeros except for like one element. Okay, so for example, let's see. Let's take, let's see, let me take this row and subtract it and add it to this row. That would make this guy 0, and that means that second column would be all zeros except for that one, right? So let me do that. So let's do, okay, so here, I'm not gonna copy all this out again. Okay, so we're gonna do row 1, 2, 3, 4. Replace it with row 4 plus is it plus row 2? Yeah, plus row 2. So that should give me all zeros there. Yeah. What is this, row 5? Alright, well, I guess. So it would be almost the same, except that now we have a 0 right here. And all this row is different now, which would be 1, 5, 6, minus 4. Okay, now let me cofactor expand this. So just take that, get rid of all this stuff, and this will equal 1 times, okay, oh yeah, and then you have to know the signs, right? So again, you can use the checkerboard, or how I do it is I just literally start off in this first position right here, and I say that's plus, and then anywhere I go on this grid, I just alternate signs. So if I go down, it'll be minus here, go to the right, that'll be plus there, so it'll be plus 1. So yeah, this will just be plus 1, so this would be 2, 1, 3, minus 2, 1, minus 1, 2, 3, 1, 5, 6, minus 4, 1, 0, 3. Oh wait, 3, 2, 0. Okay, so let's see. Okay, so maybe I should just RREF it at this point. Why not? Well, that's why, because then I'm just gonna get a bunch of fractions, and I don't want to deal with all that stuff. All right, so resizes. Okay. All right, come on, let's see. So let's do row. So row 5. Let's reduce that down to row 5 minus row 2. Yeah. You know what? So what time is it right now? 40. Okay, so yeah, I should have. I think what I should have done is done 2 row operations before doing the cofactor expansion. I should have first done what I did first. Well, I mean, you can. So row 2, not. What if we add to row 2, not row 4? I mean, it will still give us a. What? No, hold on. You know what? I'll come back to this example next time. Let's not worry about this. I kind of, I think I believed in myself too much and to be able to do this. So let's forget about this for right now, and I'll do it next time. Because I just wrote it down and I was like, oh, I can do this. It's no problem. And like I said, when you're up here and you're like speaking to a crowd of people, you're just like, it's better to not think and just have notes. But yeah, so let's just forget about this for right now. We'll do it next time. But I just basically want to illustrate that this this new ways that we learned allows us to at least be able to compute something that size in a reasonable amount of time by hand, right? All right, so all right, so let's finish off. Okay, so that finishes the section, but we'll still come back to the example later. But now let's talk about more properties of determinants. All right, so we can use these properties to be able to further simplify our work. Okay, so let's do section 3.3, properties of determinants. So, okay, so what do we want to do? So let's first pose some question like this. What if I wanted to find, let's say, A times B? So if I wanted to find the determinant of a matrix A times B, naively, what would I have to do first if I didn't know anything else? I would have to multiply A times B first and then take its determinant, right? Well, it turns out we don't have to do that. Answer, like naively, multiply A times B and then compute, right? A time and then compute this. So, however, we can do better. So let's do theorem 3.3.1, okay? So let's say you had A and B, then the determinant of A times B is simply the determinant of A times the determinant of B, okay? So the determinant is multiplicative, right? So you can just take it out. So, I mean, so now you can see that then the answer up there, it's a little bit more simple, right? You can just take the determinant of one and then multiply the determinant by other. So now we're going to basically discuss a bunch of results that will help us in many ways, all right? So now let's do another theorem. 3.3.2. Let A be a square n by n matrix and C be a real number. Then the determinant of C times A is equal to C to the n power of the determinant of A. So how you can show this one is actually pretty simple. So remember how I factor out a 7 from the row and I just pull it out to the front of the determinant? But it was only from a single row, right? So, but since this C times A is being multiplied by every row, I'm technically taking out a C out of every single row. And how many rows are here? N of them. So I'm taking out n C, so that's why we get the C to the n. And then here, where is it? And now here's a good theorem to also know. So one of the challenge questions can actually be solved with this theorem, like almost with no effort. So let A be an n by n matrix, then A is invertible if and only if the determinant of A is equal to 0. So remember how I mentioned that the determinant was stood for being able to determine whether a system has a unique solution or not? Well, if A is invertible, what did we say that about our solutions for a linear system? They were unique, right? You only have one. now we can determine that based off this determinant thing. So if the determinant of that matrix A, or the coefficients of the systems of linear equations, is 0, then we know for sure that our system has a unique solution. And not only that, but our matrix also has an inverse, right? So that's a good one to know. Okay, and then for the last thing, we'll do this. Theorem 0.3.4, and this will be the last one I do. So if A is an n by n matrix, is, let's say, invertible, then the determinant of the inverse would equal 1 over the determinant of A. Okay? So let's actually take, I guess since I have like 3 minutes, this is actually just prove it. It's actually not that big of a deal. So let's see. What can we do? So first, note this. Note that the determinant of the identity, so remember the identity, what it is. What do you guys think the determinant of that identity is? Yeah, 1, right? It's triangular, yeah, exactly. So it's triangular, right? It's just a diagonal, so you just multiply the diagonal right across, and they're all 1s, so perfect. Now let's observe this. Observe that. Okay, so now observe this. So let's take the determinant of A, and then multiply by the determinant of A inverse. Okay. What do we know about this? Well, according to the previous theorem, we know this, right? So we can combine these two to be 1. So now we have this. The determinant of A is just equal to the determinant of A times A inverse. Now what is A times A inverse? Huh? Yeah, the identity, right? And what is the determinant of the identity? Well, 1, right? What this just means that the determinant of A times the determinant of A inverse is equal to 1. And just divide both, yeah. Hold on, let's see. It's a good point. So hold on, let me think about that. So hold on, did I state that right? Hold on. Yeah, because you're right. In that case, then the determinant of A is 0, and this is just 0 equals 1. Obviously, there's something bad going on here. Okay, so hold on. Let me think about it. So if we have A and its inverse exists, then yeah, the determinant of A has to be 0. That's, oh, wait, no. It's non-zero. Non-zero. I'm pretty sure. Yeah. That's determinant is non-zero. Invertible. Yeah. Hold on. Yeah. So if it's 0, that means it's not invertible. If it's non-zero, then it is invertible. Yeah. So this is actually the correct statement. Yeah, good catch. Because then then just breaks everything else that we're about to do. But yeah, from here you can just see then the determinant of A inverse is equal to 1 over the determinant of A. Yeah, perfect. All right, so next time we'll just do a bunch of examples, putting all these properties together, and also the previous example that I thought I could do, but I guess I couldn't. All right, I guess any questions? Yeah, and I will give you guys the notes here. Export all. I'll do it here, so you guys can like watch me and not say I will do it and then not do it. Perfect. So, remind. So let's go to announcements in your algebra. Next file. Let's go to what's today. Sorry, I think